I love the look of paper cut light boxes. The intricate silhouettes, the layered depth, and the lighting work together to create an awesome effect. While the standard single color lighting looks cool, I got stuck on the idea of using controlled lighting to create a dynamic scene that can simulate a full day and night cycle. Then, with an Arduino and a bit of programming, I could sync it up with the real-time sunrise and sunset times, as well as the current moon phase. My brother lives in Philadelphia, so I thought using the Philly skyline on this project would make it an awesome gift for his apartment. For the design, I found a photo of the Philly skyline. I tweaked it so that the buildings would show up better in a 2D silhouette. Then I traced the 3 layers and adjusted the colors to plan out the lighting for different times of day. When making anything, I try to tackle the biggest unknowns as early as possible to prove the concepts before getting too deep into the project. In this case, getting a bright sun and moon to travel across the sky was the most obvious challenge. I had a few ideas, but the most promising one was to use a small screen attached to a servo arm that could move it across the sky. The servo control was pretty straightforward. Most of them rotate 180 degrees, which is perfect for this project. I hooked up a 1.44-inch TFT screen to the Arduino Nano and got the test programs running. Then I quickly programmed a basic crescent moon shape by drawing a white circle and an offset black circle over top. To see how well the screen would work in the finished product, I made a quick prototype. I printed the layers out on cardstock and cut them out with an X-Acto knife. Then I cut spacers from foam board, hot glued the edges, and taped them into a rough assembly. I strung through an addressable WS2812 LED strip and wired everything up, then ran the test programs for the LEDs. I was really excited to see how cool it was looking so early in the build. But when testing the night scene, the moon was way too dim, so I knew there was plenty of work ahead. I figured if I could make a brighter backlight, I could solve this problem. To test this, I peeled the screen apart and held it over my phone's flashlight. This was promising, so I moved on to making an LED panel that would replace the original backlight of the screen. I tested a few LED configurations to see which would provide even lighting. Then cut some perf board and soldered LEDs on in a tight 4x4 grid. This assembly was pretty sloppy, but it got the job done quick with parts I had on hand. I finished it up by adding a 330 ohm current limiting resistor for each LED. The panel was really bright, but I wasn't satisfied with the diffusion. Also, the size of the LEDs and the distance required for diffusion would make the assembly thick, causing the whole project to be thicker than it needed to be. So I ordered some surface mount parts to make a slimmer LED panel. The soldering process was basically the same, but with a slimmer result. I hooked it up to the 5-volt power supply for a test. I was really happy with the results, and the light diffusion was better, even when holding the screen closer to the LEDs. The last thing I tried was removing the diffusion material, hoping that the light would be brighter and the paper would diffuse the light enough. Later I'll show you why this didn't work out, but the resulting transparent display was awesome. I'll definitely be using this in future projects. I designed a new holder for the screen assembly. With the thinner backlight, I was able to reduce the thickness by about 75%. Then I printed it out and removed the support material. I assembled it with the screen and backlight and set it up for another test with the cutouts and the rest of the lighting. I tested a night scene and a fiery sunset and was much happier with the brightness of the screen. The last component test was the real-time clock used to keep accurate time. Here's a demo with the date and time on the screen. When the paper moves away from the screen, there's a doubling effect. This is a side effect of removing that diffusion material, so I had to add it back. I modeled the components to mount the servo and the screen. Down here we have the servo mount, which uses its built-in mounting holes, and I modeled in this section for wire routing later on. Then we have a black aluminum extrusion that's acting as an extension for the servo arm. And then an adapter that mounts to the extrusion and the PCB of the screen to hold everything in place. I sized all of the components so that there would be a nice arc for the sun and the moon, using the cutout designs as a reference. I measured out the length for the aluminum extrusion and cut it to length with an angle grinder. I drilled some holes out in the bracket that comes with the servo so I could attach it to the extrusion with machine screws. I was doing this in my living room, just a reminder that you can make things anywhere, and you might even get breaking news updates like this.
We have 3 scoops on record for today.
Cool. Then I finished drilling the holes and tapped them for M3 screws. I printed the servo mount and the screen bracket, and then assembled all of these components. The servo is secured with some M2.5 screws, then some M3 screws fit into the holes that I just tapped. In between those is an access hole to attach the arm to the servo. The screen bracket was mounted with a single screw, and then 2 more were used to hold the screen in place. For the enclosure I went with a simple mitered box, with channels to fit the paper layers and a front piece of glass. The top and the back will be removable to change out the paper cutouts and access the electronics. I printed a dimension drawing and cut the material in about 45 seconds using a montage. I glued up the box using blue painter's tape and then applying glue to the joints that would be the bottom 2 corners, not the top 2 since the top will be removable. I glued in some blocks to strengthen the miters and also to use as surface area to screw in the back panel. The upper blocks will also help support and align the top. I marked and drilled the holes to secure the back panel. Unfortunately, I lost the footage of applying the wipe-on polyurethane finish, chiseling out the holes for the button, and cutting the front glass piece to size. To avoid a mess of wires in the final project, I designed a PCB. Based on the breadboard wiring, I created a schematic in KiCad. I have the Arduino Nano in the middle. On the left I have some inputs, the power connector, and the input buttons. Then I have the real-time clock, the TFT screen, our servo connector, and the connector for the LED strips. I chose the connector for each component based on the ones that I had on hand. I started out with an outline that I measured to fit into the box. Then I laid out the components. These rat's nest wires show where the connections need to be made based on your schematic. I routed wires until all the connections were made. Then I added a copper pour on the bottom for the ground plane and a pour on top for the power plane. After a design rule check to make sure nothing was missing, I sent it off to be fabricated at Osh Park. If you've ever breadboarded some electronics, you're just a small software learning curve away from your own custom PCB. I keep some common connectors on hand, so I'm not always buying parts to spec. I soldered the connectors onto the PCB. The white ones are JST XH and the black ones are DuPont headers. Both 0.1 inch pitch, so the hole spacing is all the same. Then for the wire harnesses, I cut ribbon cable to length, stripped the ends, crimped terminals on them, and then inserted them into the connector housings. This process is the same for both types of connectors. I used an unpopulated PCB to mark mounting holes and then drilled them out. My first idea for the back layer was to use printer paper glued to a wooden frame to keep it flat even if the screen pushes on it. Unfortunately, it got wavy over time, probably due to moisture in the glue or heat from the LEDs. So instead, I cut a piece of acrylic to size, cut a clearance hole for wires to pass through, and sanded it to eliminate reflections. I used spray adhesive to attach printer paper to it and a roller to eliminate any bubbles. To avoid light leaks, I cut a piece of adhesive black vinyl to block out all areas besides where the sun and moon will show through. I cut the LED strips to length and then soldered them together. Then I soldered wires onto the power connector and epoxied it into place. Then I printed 3 buttons, inserted them, then mounted a piece of perf board which I had soldered 3 matching switches to. Then it was time for the final assembly. Functionally, this is a dumb device, meaning no Wi-Fi or Bluetooth connectivity. You set the time the old-fashioned way with buttons, and based on the date, time, latitude, and longitude, it has enough information to calculate the sunrise and sunset times, as well as the moon phases. There's also a mode to display the time for people who like numbers on their clocks. This video is already a bit long, so I'm not going to dig into the code, but you can check it out through a link to GitHub in the description. And if there's enough interest, I might make another video going through the code and the development process. Overall, I'm really happy with how this turned out. I was a bit jealous about having to give it away, so about halfway through the project, I started doubling up on each build step so that I could keep one for myself. The only thing that might be able to make it cooler is maybe a giant interactive display.